Okay, here we have section 2.3, and we want to look at this idea of a recurrence relation. And really, all that's going on there is I am going to define a sequence of things based on what came before. Okay, so the simplest recurrence things are just I look at what happened before, and then I do some rule based on what was there. And so, for instance, if you just said, well, how do I generate the odd numbers? So odd numbers. Okay, well, I can think of it as, one. I start with 1, so I started with something. So odd, I guess positive numbers, right? So start with something. I need to tell you where to start. But then I get the next odd number simply by adding 2, right? 1, 3, 5, 7. And, if I'm way up here at 21, I can tell you the next number is 23. And because I just keep adding 2 to it. So, what's our, you could write this out sort of in English. We say start with 1, then generate a sequence of numbers where the next number in the sequence is found by adding 2 to the most recent number in the sequence. Now, this is where, algebraic language is, so much better. I mean, this is about as simple as it gets, right? I mean, I start with 1, and then I add 2 to get 3, and add 2 to get 5, and add 2 to get 7. All right, but it still took me quite a bit to write that down. Well, something much quicker would be if I thought of it as a function, and a function of n, where n is the place in the sequence, right? So here's the place in the sequence, and I could start with 1, or I could start with 0, or heck, I could start with -32 if I wanted to, but let's start with 1 in this case. And then 2, 3, 4, 5, 6, 7. And here's the sequence. 1, 3, 5, 7, 9, 11, 13. Now, you could come up with a nifty function, and this is just a linear function, and you could take 2 of these points as a, you could say this is x, this is y, and you could come up with a function of the sequence number based on place. Yep, you can. But this idea of a recurrence relationship is an interesting idea, and actually for some patterns, it's really about the only decent way you're going to truly describe them. And that's just, well, think of it as we know where we start, and we know how to get the next number. Okay? And so n is our place. So as I look at something, I think of that as our place. So you could think of, instead of x, think of n up here. And then our sequence is f of n. And like I say, I could get a y equal mx plus b sort of formula for this, this sequence in terms of the nth number, right? 1, 2, 3, 4, 5, 6, you know, I want the nth number. And, you know, as I look at it, it's really not too hard, right? If I take 2 times n and subtract 1, I get the number in the sequence, right? So 2 times 6 is 12. Subtract 1, I get 11. Okay, so it's 2n minus 1 is a functional kind of, a direct kind of definition. Okay, but a different way to define this sequence is the way I'll determine, and you know, you can do this a couple different ways. I think your textbook does it with the n plus 1 thing. Let me, I have to look back at, yeah, they use k plus 1, but so my f of n plus 1 in this case, I can define that as f of n, so my previous number in the previous place, and then plus 2. But under this definition, I do have to tell you that f of 1 is 1. But then notice if, okay, so I have f of 1 is 1. And then f of 2, which is f of 1 plus 1, well, according to this recursive formula or recursion relation here, recursive relation or recursion, that means it's f at 1 plus 2. But I know what f of 1 is. It's 1. So that's 1 plus 2. I get 3. And then f at 3 is f of 2 plus 1. And so that's f at 2 plus 2. And f at 2 was 3, so that's 3 plus 2. I get 5. All right, and that's matching up nicely. 1, 3, 5 for the first, second, third spot. And f at 4 is f at 3 plus 1. That's f at 3 and then plus 2. And this is f at 3 was 5, so that's 5 plus 2, and that's 7. So that is a recursive formula. One that's a little trickier is, well, now I've just lost the name here. The Fibonacci sequence. There we go. Fibonacci, because that's based on the 2 previous values. So it starts, you can either start it at 1 and 1 or 0 and 1. Either way will get it going. But the sequence is, if I start at 1, it's 1 and 1, and then the next number is 2 because 2 came from 1 plus 1. Then I take these two numbers, 1 and 2, and add those together, so I get 3. And then 2 and 3, I get 5. And then 3 and 5, I get 8. And then 5 and 8, I get 13, and so on, so 21. So in this case, I would say that my f of n, well, actually, I'll write it as f of, you know, and should I do n plus 1 or n plus 2? See, it doesn't really matter, because the way I read this is the value here is equal to the previous value plus the value previous to that one. That's how I read the indexes, the n plus 1, the n, and the n minus 1. And so then, to get this started, I need to tell you that, and in this case, I might actually use 0, 1, 2, 3 for whatever reason. You know, I might start at 0 and then 1. You know, so I might tell you that f of 0 is 1 and f of 1 is 1. And so then, my next number, I want f of 2. But according to this, f of 2 is f of 2 minus 1, or the one before that, so f of 1, plus f at 0. But f of 1 is 1, and f at 0 is 1, and so I get 2. And then f at 3 is f at 2 plus f at 1. And so f at 2 we just found, that's 2, plus f at 1 we were told that's 1. And so we get our 3 and so on. And that is a recursive relationship. Now I use the f of x or f of n or f of k notation. They use subscript notation in the book. Now, subscript notation, that's the right, I mean, you know, it's a good notation, and part of it becomes a context thing. But let's look at this subscript notation for this stuff, because people really get confused by it, I think. So subscript notation, it's really just the f of n, right? So now, typically when we talk about a sequence, they all of a sudden switch to a's instead of f's. You know, but, okay, so let's kind of look at a progression here. So I could talk about f of x, and everybody, oh yeah, I know what that is, f of x, I get that. If I see f of x, I know what's going on. Okay, and, well, then our next progression was, well, we're going to talk about f of n. And that kind of makes sense, because if I see this, I think, real number. And if I see an n, I tend to think integer. Now, there's no hard and fast rule that that's what it's supposed to be, but sure, yeah, that's a contextual thing. We try to use n's and m's and i's and j's and k's when we're talking about integers. And we tend to use x's and y's and w's and v's and so forth when we talk about real numbers. And so, sure, okay, that just helps me clue in as to what's going on. But now, well, f's not, you know, I mean, you've used f and g and h and things like that. Well, okay, use a. So a of n. So when I see an a, that kind of clues me in to thinking of maybe they might be talking about a sequence or something like that. Okay, so it's just a clue. And now, here's the big leap, is instead of a of n, I'm going to put it down here, we're going to say a sub n. And this means a of n when we're talking about sequences. Okay, it's a synonym for a of n like that. So we say here a sub n versus a of n, but again, they are synonyms for in this recurrence relationship. And so, you know, as we look at something like that, it still works, and this is where people can get a bit confused. And, you know, sadly, some of it is people aren't necessarily really great with this notation, right? You know, so there's a big difference between f of x plus 1 and f of x plus 1, right? That's a huge difference, and hopefully you agree that there is a huge difference there. Now, you know, I kind of call this the Las Vegas rule, okay, because, you know, I look at it as what happens in parentheses stays in parentheses. Okay, so that's why I call that the Las Vegas rule of parentheses in function notation, right? What happens inside those parentheses stays in those parentheses. That's something very, very different than saying this f of x plus 1. Well, since the subscript here, when I use this notation, is really just the same thing as there. So now we have the Las Vegas rule for subscripts for this recurrence relation notation. And so, you know, what happens in the subscript stays in the subscript. Oops, subscript. Okay. And again, that's very important. So, you know, a sub n plus 1 is very different from a sub n and then plus 1, like that. Very, very different things. And this is talking about a function. It's a function of, you know, this index thing in n and n plus 1 and so forth. But a great way to internalize and kind of get used to it is, you know, in this case, when I'm dealing with these recurrence relationships and sequences of functions built on each other, then, you know, I just kind of look at that as place. You know, it's the n plus first place. And when I see, you know, if I look at a sub n minus 1, a sub n plus 1, you know, I just say, well, okay, so a sub n, maybe I'll focus on that, and then that's the element previous, there's the element after. You know, the a n plus 1 is the element after a sub n, and the element a n minus 1 is just the element previous to a sub n. And I just kind of look at it that way. So this is the idea of a recurrence relation. So you tend to see recurrence relations written more like, you know, say something like a sub n plus 1 is equal to, say, you know, 3a sub n plus 2, you know, something along those lines. And then you'd be told maybe a sub 0 or a sub 1 or something like that. You know, so if I told you a sub 0 was equal to 0, right, then I could build the rest of this thing. So I've got a sub 0 equals 0. A sub 1 is equal to 3 times 0 plus 2, or 2. A sub 2 is 3 times 2 plus 2, which is 8. A sub 3 is 3 times 8 plus 2, which is 26, and so on. And you know, and so you see, all I'm doing here in that a sub n plus 1 as I think about this is I just realize, okay, to get my next number, I need the previous number, which I got right there, and multiply it by 3 and add 2. Okay, that gave me 8. Now, to get the next number, I need to take that previous number, the 8, and 3 times 8 is 24, plus 2 is 26, and so on. Okay, so that is a recurrence relation. And based on those, you can get formulas, say, all in terms of a sub 0. So suppose I didn't know what a sub 0 was, and I take this and I've got, a sub n plus 1 is equal to a sub n, 3a sub n plus 2, and, I just know that I'm starting with a sub 0. Oh, well then I can still tell you a sub 1 is 3a0 plus 2, and a sub 2 is 3a1 plus 2, but a1 is 3a0 plus 2, and then plus 2. So I can write that as, 9 a0 plus 6 plus 2. Now, I might want to keep that like that. I might want to write it as 8. I might want to write it as 6 plus 2. It's, it's kind of hard to say sometimes, because then if I go to a sub 3, well, that's 3a2 plus 2. Well, but that's 3 times, and a2 is 9a0 plus 6 plus 2, and then plus 2. And so this is equal to 3 times 9 is 27, a0, plus 3 times 6, well, that's 18, plus 3 times 2 is 6, plus 2. Now, actually, given I've done a few of these, what I realize is, a better way to I might write this is that 27 I got from 3 cubed a0. That 18 I got from 3 squared times 2. That 6 I got from 3 times 2, and then finally plus 2. And so if I look at it that way, when I go to a4, which is 3 times a3 plus 2, what I realize I get, is I'll multiply all of that times 3, so I'll get 3 to the 4th a0 plus 3 cubed times 2 plus 3 squared times 2 plus 3 times 2, and then I'll have that plus 2. And so, I can get this all as a nice formula in terms of a0. And, well, I'll call it a nice formula. 3 to the 4th a0, and then plus, I've got a 2 in each of those, so I'll factor that out. And then what I've done is I've summed, and I'll use say a k equal, I've got 3 to the 0 here, and that's what I'm looking at the powers of that. So I got k to the 0, or k equals 0, up to, and I go up here to this 4 minus 1, so I'm going to write that as 4 minus 1. I go to 3, and this is 3 to the k. And so now I can actually tell you that, if I want a sub n, that's going to be 3 to the n a0 plus 2 times the sum k equals 0 to n minus 1 times, or of 3 to the k, the sum of 3 to the k. Whew! Okay? But, I can get these in terms of a0. Now, it's not always, easy to get that. I mean, because when you think about it, this is a relatively complicated looking thing. And heck, my recurrence relation was simply multiply by 3 and then add 2. Right? And so when I get this in terms of a0, it starts looking kind of complicated. Okay, but that is what a recurrence relationship is. And your text doesn't really go into it much. It just kind of throws it there at you. If you've had discrete math, maybe you've seen recurrence relationships there. Possibly in a couple other places along your math career. But there's also a reasonable chance you really haven't seen these before. And so this is something a little new. So that is a recurrence relation.